Okay, so today we're going to look at the derivative of x to the power of n. So our learning intention is the knowledge of how to differentiate functions where there's an x value to a power of n and other functions of similar constructions. So we'll be successful if we can correctly differentiate f of x equals x to the power of n, or f of x equals k to x of n, or k x n plus 2 plus or minus k x to the power of n plus 1 plus k x to the power of n plus a constant. Okay. Now, when we had a straight line in the form of y equals mx plus c, so here we have a function where the highest power of x is 1. We knew that the gradient of that function was m, or y dash, or dy dx, is m in this case. So we're going to continue on that understanding and apply it to other situations. So the derivative of dx of k to the x is going to be k. So we have it like y equals mx plus c. So an example would be, what would the derivative of 3x be? Well, in this situation, it will just be 3. If we have d over dx of k, of a constant, well, where there's no power of x, so for example, if we have, let's keep it with 3, well, the derivative is 0. Yeah, there is no gradient at that point. If we had the derivative of x to the power of n, well, the derivative of that is going to be n x to the power of n minus 1. So for example, if we have something like this, d of dx of, let's say, x squared, right? So it's going to be 2 is n, so it's going to bring the power down, keep the x, and reduce the power by 1. So 2 minus 1 is just 1. We don't need to even bother writing that. It's just going to be 2x. All right. Now the derivative, so d of dx of k x to the power of n is going to be kn of x to the power of n minus 1. So that's like this. So let's say we have 3x squared. Right? We bring the power down and we multiply it by this constant. So 2 times 3 is 6. We keep the x, and now we reduce the power by 1. So 2 take away 1 is 1. We don't really need to bother writing that. Okay? And obviously the last part is that if we have the derivative of k of a function, so a function being multiplied by a scalar, well, that's going to be k multiplied by the derivative of the function. Okay, let's do some examples. So if we want to differentiate x minus 3, right? So let's say y dash, okay? Here we have a power of 1. We're going to bring the power down, and then reduce that power. That's going to be 0, and so that disappears, right? Or x to the power of 0 is 1, so 1 times 1 is just 1. 3 is a constant, and so we don't differentiate that. Alright, this one. With this type of differentiate, we can differentiate each section by itself. So here, we're going to bring the power down and multiply it by 3. So 2 times 3 is 6. We keep the x. We reduce the power. 2 take away 1 is 1. So that's 6x. And here we've got 1. 1 times 2 is 2. Reduce the power, x to the power of 0 disappears. Okay. Once again, so y dash, or dy dx. Bring the power down and multiply it by the number in front. So 2 lots of a half is just 1. And reduce the power. That's just 1. That's 1. Bring the power down, reduce by 1. So that's going to be the derivative of a half x squared plus x plus 4 is x plus 1. A constant has nothing, is 0. Something like this, what we can do is we can expand. All right, so we've got x times 2x is 2x squared plus 3x. So if we differentiate, we've got 2 times 2 is 4, reduce the power. 1 times 3 is 3, reduce the power. Okay, something like this we can expand. We've got square the first term, multiply them together, then double it, and square the last term. If we differentiate that, we get 2x plus 4. Once again, here this example, we expand out. We've got x squared plus 4x plus 3x plus 12. Collect like terms. Now if we differentiate, we've got bring the power down, that's 2x reduced by 1. Bring the power down, reduced by 1. The derivative is 2x plus 7. Okay. Let's say we want to find f of x. If f of x is 2x to the power 5 minus 3x to the power 4 plus 6x to the power 3 minus 2x to the power 2 all over 3x squared. Well, the first thing we want to do is we really kind of want to split everything up. So f of x really is 2x to the power 5 over 3x squared minus 3x to the power 4 over 3x squared plus 6x cubed over 3x squared minus 2x squared over 3x squared. Now we can cancel things out. So that's 2/3. That leaves us x to the power of 3. 3 cancels out. That's just going to leave us x squared. That's going to be 2 to the power of x, 2x I mean, and that's going to be 2/3. That's f of x. So if we're going to differentiate that, f dash of x, so 3 lots of 2/3, we get 2, reduce the power down, will be 2. Bring the power down, 2, reduce the power, that's 1. And now it's just going to be 2. And the constant disappears. Okay. If we want to find f dash of 2 for this problem, what we're going to do is we're going to substitute 2 every time we see x. So that's 2 lots of 2 squared minus 2 lots of 2 plus 2. So that's 4 times 2 is 8, minus 4 is 4, plus 2 is 6. Okay, so we're just substituting 2 every time we see x in the derivative function. Okay. Now we also don't, we've used a lot of dy dx and differentiated in regards of x, but now we're going to differentiate in different variables. So if we're given v equals 4/3 pi r cubed, we want to find the derivative of v in terms of dr. So the change in v over the change in r. So dv dr, we're going to bring this 3 down. So 3 lots of 4 over 3 is 4. Pi just stays there. That's just a constant. And we're going to go r squared. We're going to bring that power down. Okay. Now, given that we've got h of 0.2 t squared minus 0.15 t, we want to find dh dt. We want to find the derivative of t in respect to derivative of h in respect to t. So we're going to go 2 times 0.2 and reduce the power. 1 times 0.15, reduce the power. And that's the derivative. So we want to find dv dt of that should be v dr when r equals 2. Yeah, what we're going to do is substitute 2 into that. So that's 4 times 4 is 16 pi. If we want dh dt of 1, we're going to substitute 1 for every time we see t. And we get a solution. Okay. And that's differentiating differentiating x to the power of n. Thank you very much.